Thanks for coming back and thanks for the wait. Prateek, please take it away.
Thank you. Okay, so thank you for joining this session again after the break. So let me just quickly recap what we saw in like last hour or so, which is that we looked at linear regression mainly. And we said that, okay, if you have IID data, one pass SGD is good. But as soon as you start having some kind of dependencies between your data points, then there are some issues with SGD. And for some very specific setting around like, a particular type of Brownian motion setting, we were able to show that techniques like experience replay, which are used in practice quite a bit, can be quite helpful, like, from regress theory standpoint of view also. So in this, remaining 45 minutes or so, I will build upon these things, and I'll try to sort of, I'll show you how we can study some standard problems like, say, linear dynamic system, non-linear dynamical system, and more interestingly, Q-learning with for reinforcement learning. For those problems, we can build upon these experience replay ideas, add some more ideas like reverse experience replay, and show that you can get much nicer results. So, so let me introduce linear dynamical system. It is very similar to the linear regression setting. There are some small changes, but roughly like what's happening here is that you observe some data point xt plus 1, which is given by some matrix A times xt plus epsilon t. Let's assume that all our data points are in d dimension. So this A star now belongs to d by d dimensional space, right? And for simplicity, we are assuming that epsilon t is sort of independent noise. That is, it's a zero mean, and it is independent of all the points that you have seen so far. Right? And what's the goal? Goal is given these data points x1, x2 till xt, so you have a single trajectory of points. You want to estimate A star from these points. Right? So this again we can write as a least squares problem. So the the problem is that given some xt from say the stationary distribution, we want to find an A so that this loss is minimized, right? And you can write a ERM version or like empirical risk minimization version of this for your sample data points, right? And here again, now you can try to solve this problem with stochastic gradient descent. The stochastic gradient descent will look something like this. That is, your matrix AT is given by AT minus 1 minus some step size times the gradient, right? So gradient has this sort of loss term AXT minus XT plus 1 plus times this vector XT transpose, right? And one thing which is sort of fairly easy to see, we don't need to run through those calculations here, but given AT minus 1, this gradient is not equal to the true gradient that you want. So basically SGD has bias in some sense. And the whole thing comes because your AT minus 1 is dependent on x1 to xt, and because xt and xt plus 1 are correlated with each other, you have this sort of dependency. This sort of slide tries to make that point. Let me just skip this. So we had already talked about this concept of mixing time, which is that mixing time is roughly just how many points I need to skip or remove before I start seeing almost IID points. That's what we do. And again, you can use for for this problem also, while SGD might not work, but you can do SGD with data drop, and you will pay this tau mix extra factor for that. Right? So this we have seen, but let's sort of explore this new idea, which is that we will do experience replay as we talked earlier for SGD, because we have seen that experience replay can improve our rates in some interesting manner. But here, rather than using this uniformly at random experience replay, that is within a pool, rather than taking points uniformly at random, we will process them in the reverse order. So let me sort of go over that. So suppose this is the set of data points that we are getting. We break them into these buffers. Between the buffer, there is some sort of gap, right? And think of this gap again as sort of almost like tau mix, so that individual buffers are independent of each other, right? Now, earlier what we were doing was we were taking this buffer and we were sampling points uniformly at random from this buffer, right? But for solving these linear dynamic system kind of problems, we will not do that. We'll process this buffer in reverse order. That is, in the buffer, we will first take this point, process it with SGD, then we'll take this point and process with the SGD and so on. So we will go in the reverse order, right? And like I think intuition will become clear once we write out a little bit of this math. But one thing you can sort of, I guess, I can sort of intuitively reason is that at this point, when I'm taking my data point, I am just dependent on this point, right? And this has, let's say, epsilon of b because, sorry, give me 1 second. Like these epsilons are independent of whatever you have seen in the past. So it has some epsilon b where b is the buffer size here, right? So I'm mainly dependent on that. Then when I go to the next point, right? The next points are whatever x1 to xb minus 1, and they are all independent of epsilon b. So that coupling that was coming because of the noise or these epsilon b terms, that gets away, or that is sort of a zero mean quantity because epsilon b is independent of all the points x1 to xb minus 1. It will become more clear once we write out some of these equations. Just one acknowledgement, which is that this reverse experience replay was independently also proposed by Rotinov, and they showed that this leads to some very interesting, good sort of empirical performance in some practical problems. So let's look at how we sort of, for this linear dynamical system, how we can apply this SGD RER or reverse experience replay. So this is our buffer. Buffer length is B. First, let's say we process the first point, which is like the last point in the buffer. So we have some initialization point A0. A1 is given by A0 minus eta times the gradient at A0, but for this point X, right? So this is the term that you get. And then similarly, you do it for A2 and so on for AB, right? So for the bth point that you're processing here, actually you are taking the first point in the buffer, right? So once you finish this buffer, you leave a gap of tau mix, and now you are again sort of doing this processing. So you keep on doing this processing with this tau mix gap. Right? So why do we get these? So one question is why does this help? Right? So the claim is that once you do this kind of updates, then in some sense you are getting unbiased estimates of your A star. Like you're getting closer to your A star in some unbiased manner. So how is that happening? Well, if you did SGD, then SGD, the first iteration step is like this, which is okay. But when you look at the second step, AT plus 1 minus A star, and you want to look at the expectation of this, you will have this term that we get in the standard bias. That is, you have AT minus A star into this term multiplied by this term. So that was fine. So those matrices multiplications we have seen 2-3 times now. But now the issue is that xt plus 1 is dependent on epsilon t. So when you try to take expectation here, this expectation is not 0. So you have these noise terms also coming into picture here, which makes the the analysis basically this is not 0 mean, and that's why SGD doesn't even have sort of unbiased estimate in some sense. But let's see what happens with this reverse experience replay, right? So in reverse experience replay, we let's say if we are at 80, we will be processing xt minus 1. Right? Sorry, for 80 plus 1, we'll be processing xt minus 1. Which means that now the same epsilon t term is hitting only xt minus 1. And because epsilon t is independent of all the points that came before it, when you take expectation, this term goes to 0. So in expectation, basically, what we have is 80 plus 2 minus A star is 80 minus A star into these matrices that we are multiplying. So as long as we can show that these matrices in expectation have eigenvalues strictly greater than 0, we know that we will be converging towards A star, which is something that seemed much more difficult to show in SGD. So that's sort of the simple sort of intuition for why we are using this reverse experience replay, that is processing points in reverse order. So based on this idea, this is the result that we can get. So what we can show is that we will be able to converge to A star So we obtain some A hat, which converges to A star with this kind of error rate. So earlier I was sort of showing all the errors in squared norm. Here we don't have squared norm, so that's why there is an additional root. But the term looks very similar. That is, we have d sigma square by t, and this term is basically dependent on the smallest eigenvalue of the covariance of the Gramian matrix, which we cannot sort of avoid, because here we are estimating the parameter error. So this you cannot avoid it. So this is information theoretically optimal rate, which is proven by Simchovitz in 2018. And this is sort of the first streaming algorithm to sort of get this rate. And actually, we can also extend this analysis to nonlinear dynamical system. So here we have a linear dynamical system, that is xt plus 1 is exactly equal to a star xt plus epsilon t. But in many settings, your system are not linear, you have nonlinearity. So suppose xt plus 1 is some nonlinearity sigma of a star xt plus some noise. So even in those cases, we will be able to solve the problem. We'll need to make some assumption about nonlinearity. That is, nonlinearity should not be completely flat at some places, because that becomes problematic. Otherwise, we'll be able to. Good question. So here I am not doing full analysis, right? Like this is within a buffer, right? So within a buffer, I have once you put this reverse experience thing, you have multiplication of these things coming in, right? But to bound this expectation value of this is still somewhat tricky, because xt is dependent on xt minus 1, xt minus 1 is dependent on xt minus 4. So we do that analysis using some simple AMGM inequality and all. And that's why we don't want to do it for very large buffer size. We want to ideally do it for some specific buffer size, then leave a gap so that the next buffer is completely independent of this buffer. So that's the thing. Did I make it clear? So basically, yeah, this analysis can work for very large buffer sizes. We want to keep buffer sizes to be as small as possible for memory constraints. And because by making this buffer size small, we are able to get the correct sort of error rates. So, and the gap is clear, right? Because for doing any of this analysis, especially around variance analysis, the only tool that we have is you do an averaging, and you will you have independent noise, and you'll be able to decrease the error. But if your buffers are not independent of each other, we will not be able to do that averaging properly. So that's why that gap is very. Any other questions? Okay. So yeah, so this is the rate we can get. As I was saying, we can get it for nonlinear dynamical system. That is, there can be a link function sigma or nonlinear function sigma that can sit on top of this. But we will need to make some additional assumption about the nonlinear function also. Right? And this is what we see empirically. So here on the x-axis, we have plotted the number of samples that you're processing. Y-axis, you are plotting the error that a method gives. And this is the error you can get with purely offline methods. That is, if you have seen all the t points, then you can sort of get these kind of error rates. And here, if you just apply standard SGD, its error sort of saturates much earlier. It is nowhere close to the error that your offline methods can get. If you apply standard experience replay, that also seems to saturate much earlier. Whereas if you apply this reverse experience replay, we are able to get to almost the same error, but in some sense much faster rate. Can I put battery? Do you have a USB-C charger? USB-C, any chance? I have USB-C, but I need to get it. Sorry about that. My battery, the laptop ran out. Go ahead. Yeah. Mhm. So that's why we want to restrict the buffer size to be as small as possible. Our current analysis requires it to be larger than order tau mix. There's some log factors there, but currently we need it to be at least tau mix. Any other questions? Okay. So, so building upon this sort of linear dynamical system and non-linear dynamical system stuff that we have, let's try to see what sort of results we can get for Q learning with reverse experience replay. So we'll switch gears. We will move to these MDPs and running Q learning methods on top of it for estimating policies. So Q learning is a sort of super popular method for MDPs and estimating optimal policy for MDPs. Has been studied since 30 years. There are some convergence issues that also people have shown in certain settings, like say linear MDPs. In practice, people do not use standard Q learning. They use it with some additional ingredients like online target learning and experience replay. And at least for online target learning, some prior work showed that it helps with some stabilization, but experience replay was not very clearly studied in any of these settings. So our sort of main punchline is that we are able to introduce this idea of reverse experience replay along with this target learning, and we can sort of provide first sort of analysis for Q learning for linear MDPs. We can show that Q learning when applied to linear MDPs does give fairly good result. We also obtain some interesting results for the tabular setting. Let me describe what all that means, but this is sort of the punchline. So let's consider, let's start with a tabular MDP system. So suppose I have a finite number of states, finite number of actions. When you are in some state ST, you take some action AT, you go to some new state ST plus 1, and you get some reward RT plus 1, right? So the MDP can be essentially be described by these two sort of matrices. So one is that if you're in a state, if you take some action, what is the probability distribution of other states that you go to? So that's one. And the second thing is that if you are in a state and you take some action, what is the expected reward you get out of the system? So those are the two key things that you have to sort of worry about and estimate in some sense. And the goal is to come up with this policy, which says that for a given state, what is the set of actions I should take? What is the action that I should take so that I can sort of maximize my cumulative reward? So reward, here I sort of, told you about one-step reward. That is, if you are in a state and you take some action, you get some reward RT, and you can sum all that reward to get your cumulative reward. For a certain point, you can sort of add some kind of discount factor in this cumulative reward, and you can say that, okay, I will try to maximize this cumulative reward with this discount factor gamma. That is, if I am getting some reward, much further in the future, I will not pay much attention to it. I want to do reasonably well in sort of recent, in some next few steps. And the goal is to find this policy, which essentially means a probability distribution over actions for a given state that maximizes this cumulative reward. All right. So initially, let's think of this as tabular setting only. That is finite state, finite actions. So here, Q value based methods are super popular. So Q value function is essentially a function that maps state comma action pair to some real value. And intuitively what it does is it computes the maximum expected reward for a given state comma action pair. That is, if you are in a state and if you're going to take some action A, then what is the maximum reward you can hope to get? That is what your Q value function captures. And there is this very nice sort of Bellman equation, which tells you how this Q value function looks like. Basically, Q value satisfies this stationary, fixed point equation. That is, if you are in a state comma action pair, you get some reward R, right? And then you you have some distribution or going to some new state S prime. And then you say that, okay, in that state, I will try to figure out what is the best action I can take. That's what my Q star should satisfy. So this is the fixed point equation that your optimal Q value function satisfies, right? And then there's this very nice Bellman theorem, which says that a optimal policy, a policy is optimal if and only if it is induced by a Q value function. That is, if the distribution that you're getting, right, if it is sort of, in the, its support is it in the argmax of this, then only you have an optimal policy. Otherwise, you cannot have an optimal policy. So this essentially, like this Bellman theorem essentially says that if you can estimate Q value function optimally, you can read out an optimal policy from it very trivially. Right? So the main goal is to solve this or find this Q value function. Now, because this is a fixed point iteration towards, or fixed point equation to which we want to go for, you can say that, okay, I can have this Bellman equation which tries to approximate Qt plus 1 with current policy. So suppose I have some current policy Qt. Based on that, I can try to get the next sort of policy. Right? I will try to approximate it like this. That is, Qt plus 1 I can think of as my parameter. And I have some current parameter Qt, and that gives me this target. Like this is the target value. So this is almost like a linear regression kind of problem. That is, I have some target value based on my current Qt, and these are the parameters I need to estimate. And I can try to do again a simple least squares regression here. And if I do say a stochastic gradient type of update here, this is essentially what I get. So I will get Qt plus 1 ST80 is equal to 1 minus eta Qt ST80. Like this eta comes because of the learning rate and the gradient term, and plus this kind of term. Right? And yeah. Oh, sorry. Good catch. So I should have a discount factor here. Like, it should be plus gamma here. Thankfully here I have. And what you can show is that, like it's well-known result that for at least finite finite state MDPs, when t goes to infinity, Qt plus 1 converges to Q star. Okay, so now let's look at, so this is like the situation for your tabular MDP or finite state MDPs, where you have finite set of states and actions. But let's look at more general version of it, which is linear MDPs, which is also sort of really popular in modeling these MDPs, where you want the number of states and actions to be infinite. So here, the idea is that for a given state comma action pair, you can describe that using a feature vector phi. And in addition, you have a feature vector psi for each state, right? And now the transition matrix, that is given state and action pair, what is the next state you go to? Like what is the probability of going to some other state? That is given by this vector, this linear form. So it is given by inner product of your feature vector for the state comma action pair multiplied by the feature vector of the state itself, right? And similarly, your reward for given state comma action pair is also a linear function of the feature vector. So it's a purely linear MDP. And in general, for these linear MDPs, what we know is that there are some methods, efficient methods, both from complexity theory point of view, or sample complexity point of view, as well as computational complexity point of view, which are able to estimate the correct policy, right? But what we didn't know was how Q learning works in these kind of settings. As in, there were some examples which showed that Q learning might diverge for when you apply it to linear MDP. So first, let's see how Q learning can be applied to linear MDPs. So the Bellman equation that we had earlier in this linear MDP case reduces to this nice fixed form, right? So here what we are saying is like this is essentially the Q function for, so Q function is parameterized by W star, and this is essentially the Q function for ST comma AT pair. And what we are saying is it has like, very much the same recurrence here. Again, I'm missing a gamma factor here, sorry. Right? And if you want to apply a Bellman iteration now, what you want to sort of say is that this parameter W, I want to approximate it so that this inner product is close to this target value. So based on the current policy WT that we have, current like, Q function parameterization WT that we have, you can get a target value, and then you want to find a W T+1 that approximates that. So you can again put sort of a least squares loss on this, and you can do SGD style update, and this is what you'll get. So this is your sort of Q iteration for linear MDPs. It's fairly easy to see. And as I was saying that back in 95 itself, Baird showed that for linear MDPs, the standard Q learning can diverge. Like there are some examples, it can diverge terribly, right? And even when you apply Q learning for tabular setting, like in this vanilla form, it doesn't give you optimal bounds. That is, min-max optimal bounds have this form, like 1 by epsilon squared times 1 minus gamma to the power 3. That is, gamma is the discount factor here. So this is min-max optimal bound. But Q learning sample complexity bound, even in the tabular setting, has this form. Right? So there is a 1 by 1 minus gamma to the power 5. And people have shown that you cannot improve that. Like it's not an issue with analysis. That is what your Q learning method gives, right? And to get this min-max optimal bound, there have been some very interesting works. In particular, there has been some this variance reduction techniques for Q learning, as well as some model-based techniques that people have introduced. So you are able to get this rate, but not with standard Q learning. You have to do something more on top. Right? But in practice, people are not using Q learning in this original form, primarily because people realize that Q learning is like this stochastic gradient descent kind of thing. There are a lot of dependencies between the data points. So you want to break those dependencies in some manner, right? And for that, there are two heuristics that are being used. One is that of experience replay, as we discussed. Another is that of online target learning. So in online target learning, what you do is rather than every time updating the target. So here, who gives the target? Target is given by WT, right? So this target is given by the current Q value function that you have, or a current policy that you have. So rather than updating this target every time, as you update your Q function, you fix the target to be fixed for certain number of iterations. That is, you say that, okay, I have some Q function right now. For let's say next 10 steps, I will use only that Q function to get this target value. Right? So that is called online target learning. So people typically use these two ideas to get around these dependency issues and all. So we have proposed a method which essentially combines them in an appropriate manner. That is, we have Q learning along with reverse experience replay that we discussed, and some sort of online target learning. And then we have a sort of more efficient version of our method, which we call QRex DARE, where we are also doing some kind of data reuse. I'll not go in detail of that, but as I said, target learning, in say linear MDP setting, this is how it will look. That is, once I fix my target policy or my target parameterization W target, for a few iterations, I will not change it. So my target value is given by a fixed parameter. For a few iteration, I will keep on doing my gradient descent with it. And then only once in a while, I will update it to the latest parameterization. Right? So how does QRex works? Well, it looks very, very similar to the reverse experience replay plus HGD plus reverse experience replay method I showed you earlier. So you have this time varying like this. You are getting these points. The points are essentially your tuples of state, action, reward, right? So you have these points coming in like that. You divide them into the buffers with some gap, and you have these outer loops where your target is fixed. So throughout this loop, I'm not going to change my target at all. Right? And within the outer loop, then I again have this buffer breakup and the gap. So now what happens is that this is how the update looks. It looks a bit ugly, but it's not very complicated. As I said, for a given buffer collection, we target, like use the same target, that is this W1 is fixed throughout a buffer collection, and we just do reverse express replay, that is these points are processed in backward manner. And in QRex there, basically what we do is we are sort of reusing the data in this outer loop itself, but that's sort of a technical thing. So based on this, what type of results can we get? So any question about the algorithm itself? Yeah. Data is collecting using? Yeah. So this is a off policy technique. Any other questions? So this doesn't have, for example, the issues around exploration and all, like those issues we have done. Like this is mainly around optimization, that okay, how can you optimize things properly to obtain the optimal policy? Yeah. That's a good point. Yeah, if you do that epsilon greedy across these behaviors, we should be able to analyze it. So far, we have not done that. Any other questions? Okay, good. So this is the result that we can get based on this technique for linear MDPs. So we can estimate the optimal policy up to this sort of error, right? So what are the terms here? So n is the total number of samples that we have seen. Kappa is some sort of condition number that you cannot really avoid. And you have this term like 1 minus gamma to the power 5. We don't know whether this rate is optimal or not, but this is the best we could get. Right? Yeah. Tau mix is of the, sorry, I didn't understand. Yeah. For the MDP. For the MDP itself, right? So for an MDP, there is, it has a Markov decision process, right? So for that entire thing, whatever is the tau mix. So this is off policy, right? That is, we have fixed a policy from which then you are generating the sample. Yeah, this is for the behavior policy. Okay. Any question about the results? Yeah, yeah. Yeah, if it is purely uniform, then yeah, you don't have it. But that I guess is very hard to get in practice. Like you will not be able to. Yeah. Any other questions? All right. So now, sorry, I sort of misspoke here. So this is the rate that we get. But now when we start doing this data reuse, then we are able to get this rate down to 1 minus gamma cube, which sort of matches what you get for. Yeah. So this is the rate you get for tabular setting, and this we know matches the min max lower bounds also. So with data reuse, we are able to get the exact rate even without using explicit variance reduction. So this is for tabular setting. Okay, so this technique, we were able to use along with some more ideas from Dheeraj and Ramnath, who is a colleague of us. So they were able to come up with a technique that combined experience replay, but it also sort of looked back and said that wherever the loss is very high, you give higher priority to those points. So by doing a combination of those ideas, they came up with this new technique called IER. So when you put that in addition to the Q learning, what they observe is that you can get much better results. So for a variety of these standard RL benchmarks, what you see is that compared to the standard experience replay techniques like UER and prioritize experience replay, etc., you are able to do much better. So this score being higher indicates better performance. So the reward is, so this is the reward. So reward being higher is good. So they are able to get a much higher reward. And in some cases, so this is sort of the most consistent method. All these methods in some cases do something reasonable, but in some cases they completely fail. Whereas this technique is also sort of much more stable. And I think Ramnath also found that this technique is not very, very dependent on the number of seeds, etc. So you can try it with a few seeds and you can easily sort of reproduce this. And we sort of attribute it to the fact that because of using reverse experience replay, within each buffer, we are able to sort of, get the error to be reasonably bounded. So that I think is the reason why you don't have very big deviations across multiple seeds, etc. Yeah. Yeah. So here the data reuse is just that, when you are going through this outer loop, we don't have to sort of, throw away the past data and use new data. So we can just reuse that data. That's the. It does. Dheeraj, you have. Okay. Yeah, and we observe similar thing for some simulations also. So yeah, in summary, we looked at this reverse experience replay technique in linear dynamical systems as well in non-linear dynamical systems. And what we observe is that in both these cases, reverse experience replay is able to get the optimal statistical rate of estimation without any dependence on these mixing time factors. We also were able to get sort of nearly optimal rates for tabular settings with Q-learning for linear, with Q-learning plus reverse experience replay. And we get sort of the first rate for linear MDPs with Q-learning by using these enhancements of reverse experience replay and online target learning. Yeah. I mean, that is not necessary. There, we are just using it as a reverse experience replay. So. No, those are not done. So that is standard formulation that people have. It's just that when you're doing your Q learning, so that has neural sort of policy approximation, it's a neural function approximation and all. So those are all there. It's just that whenever you are doing your updates, rather than using something like say random experience replay or prioritized experience replay, we have a very particular type of experience replay that we can use. Reverse experience replay. Yeah, that's not. This is just to sort of say that that idea of reverse experience replay seems quite well grounded in reality. Okay, so that's all I have. So there was this direction obviously sort of leads to variety of interesting sort of questions. So one is that so far in our entire framework, we have been assuming that the noise that you get is sort of IID given the past data points. Oh, sorry, zero mean given the past data points, which might not be true in a lot of settings. So generally sort of, weakening these assumptions would be interesting. Another thing is that the analysis that we have here sort of very closely mimics the analysis that we had for the IID linear regression case. That is, in each of these cases, we try to see if we can design our algorithm so that the form of the bias error looks very similar to what you get for IID setting. So one sort of thought is that, okay, can you sort of, get these RER results, etc., by using our SGD for IID setting as a black box rather than us doing that entire work from scratch. And then the results that we have shown so far, they are mainly for parameter estimation setting. So and that's why you had terms like this. So you had terms like sigma min of G because we are giving this parameter estimation error. But if we just care for prediction error, then such terms should not be there. So like, designing algorithms designing your analysis so that we can directly target parameter error and get sort of avoid these issues, that would be quite interesting. And finally, like, we mainly analyze reverse XPS replay. These other techniques are like, like prioritize XPS replay and all. They also have sort of quite interesting results in many cases, at least practically speaking. So one thought is that can we show that prioritize XPS replay, etc., they can also lead to some interesting gains for some standard, for say standard linear MDP or similar settings. So that's what I have. Questions? Yeah. Sir, can you come on? Yeah. So in linear MDP, you can show that there is no approximation, as in the optimal Q function has exactly this form. Like if you have exactly those same assumptions, then this is how your Bellman iteration will look. Now you can say that, oh, but for arbitrary MDPs, I can try to do this linear function approximation. Unfortunately, none of our techniques will work in that situation. And as far as I remember, there are bunch of sort of, there is a lot of further classification you can do. So I think in many of these functional approximation settings, you can get something statistically optimal efficient, but computationally efficient methods are not even known, like in general settings. So it's a very sort of interesting direction to explore. I think our techniques so far don't apply.
Why not try something like a policy gradient for a linear MDP? Just curious.
Yeah, policy gradient works for linear MDP. It's just that Q-learning is quite popular in practice, especially for when you have really large number of actions. So.
Yeah.
Okay, so if there's no more question, let's thank Prateek again.